Now we're going to move to the parallel axis theorem. Here it is. This is the equation. This is a gem. I still remember when I first sort of figured it out, like, wow, that's pretty impressive. So what you have is you can have a moment of inertia, and that bar on top, or like this bar on top, means it's for a centroidal axis. That means an axis that goes to the centroid of my area. And you can take that plus the area, the magnitude of the area, and then this is some distance between the two parallel axes. Just take a look. We have parallel axes. I have two axes that are parallel. One is a centroidal axis. The other is parallel to it, but it's not going through the centroid of my area. It's shifted off. And if I wanted to know the moment of inertia of that area about the axis, which is not the centroidal axis, but it's shifted away, then I could calculate it. It would be, give me the centroidal axis, moment of inertia, the area, and then that separation distance squared. So here's my general two-dimensional problem. I have the centroid. I have a coordinate system that's aligned. So typically you put it like x and y. The book uses like x prime, y prime. Maybe you'll see me use xc. That's not good. Just leave it x prime, y prime. Okay. Now I have another axis over here. This is my x, my y axis. This x prime, or the centroidal x-axis, has to be parallel with another axis of interest. Otherwise, you can't do it if the two axes aren't parallel. They have to be parallel. And if they're parallel, what that means is there is a constant separation distance that is the same regardless. I mean, that axis continues on. Do you see that? That distance d is constant. It's the shortest distance, the perpendicular short distance between the two parallel axes. Okay, so if I wanted to know I about this x-axis, I would get the centroidal x-axis moment of inertia. I would add to it the area, the magnitude of the area, and that separation distance squared. Powerful theorem. It's very easy to use. Here it is written for that x-axis. So I can also write it for an arbitrary y-axis. It would be I bar y prime. That's a little redundant. I mean, they're saying, look, it's a centroidal y-axis. Like this y prime is, it indicates it's at the origin of that x prime, y prime is at the centroid of my area. Okay. Plus the magnitude of the area, and then that distance in the y direction squared. Kind of very, very general. Here it's for the y, x, and here it's for the y. Whoops, I needed the right x there. The distance, like this is between the two x-axes, this is distance y. We had worked out last time by integration what the centroidal moment of inertia for a rectangular area, and it was 1/12 base height cubed. So if I say it's about this x centroidal x-axis, that's the I x of c. I can't do a typing of I bar x, okay, prime or something like that, but that's equal to 1/12 base height cubed. Somebody says, I want you to give it to me for the parallel axis, which is not going to the centroid, but is going along the bottom edge. You say, I already know the answer to that. Well, let's use the parallel axis theorem to confirm it. Okay, so the parallel axis theorem says, give me the magnitude for the centroidal x-axis, add to it the area and that separation distance squared. Well, it was 1/12 base height cubed for the centroidal. Area for this rectangle is base times height. The distance is half of the height squared. So this becomes 1/4. This is 1/12. I add those together, but both terms have base height cubed. Do you see how you have a height squared, that's height cubed? And so you multiply by 3 over 3, So you get 3 plus 1. That'll give me 4/12 of base height cubed. 4/12, that's 1/3 base height cubed. Does that look familiar? Yeah. So it works. I mean, that's how you use it. And we use it for very simple things. Rectangular strips are the best that we use them for. Okay. All right, there is the quick derivation. Now, I want to become familiar with these different coordinate systems. I find that a lot of times students can easily get tripped up. I can get easily tripped up, so we need to go slow. So what do we have here? We have an area, some general area, and we have some location where the centroid is of that area. And now going through the centroid, I have a centroidal x-axis and a centroidal y-axis. I have a general coordinate system xy. It's not tethered to anything like the centroidal x and y axis. It's off, shifted off. We shifted off down and to the left. But in this larger coordinate system, I have the xc, which is the location of the centroid of my area. Maybe this was, 5. Maybe this one's 6 or something. You can think of putting numbers there. Okay, true or false? The x prime axis is a centroidal axis. It's true. I just said it. All right, that's true. All right. Okay, true or false? Let's say somebody says that x of c is 6. And out here, x prime is equal to 2. And y sub c is 7. And y prime is 3. So I could tell that the point is at a location of x prime equal to 2, y prime equal to 3. Where's the location of the point? Right there. There's my point, isn't it? What is the location of my point in x and then in y? The global coordinate system, not the centroidal coordinate system for this problem. What is its x location? 8. All right, for the y, would it be 4, 7, or 10? 10. Now, maybe I put inches on it or centimeters, whatever, but you get the idea. So now you want to kind of write that into an equation form, and is this the correct equation form? Yes. Isn't that what we just used? So this is true. How about this one? That's true. In the x and y coordinate system, where is the location of the centroid of the area? It's at location xc, yc. All right. In the x prime, y prime coordinate system, where is the location of the centroid? 0, 0. That's a very good observation. It's a big observation. Don't forget these little things because we get tripped up. Okay? All right. True or false? xc is equal to 0. False. How about x prime of c is equal to 0? That's true. All right. How about the integral of dA? The integral of dA, is that equal to 0 for this problem? False. I mean, the integral dA is the size of the area. Isn't that just the area? It's not equal to 0. I can see it's not equal to 0. A non-zero area that I'm interested in. Okay. How about the integral of x dA? Is that equal to 0? No. No, that's false. How about the integral of x prime dA? It's true, and we really need to get to that statement because we're going to use it in the derivation of the parallel axis theorem. This is definitely true. Think of it this way. If I wanted to calculate x of c, what was my general equation? Wasn't it 1 over the area? The integral of the x tilde of the dA, it's the location x dA. So this integral is needed to calculate the location xc of the centroid of the area. All right, but if I say, give me x prime of c, that's the location of the centroid in my centroidal coordinate system. You already made the observation it's equal to 0. But just think of the equation. Isn't it 1 over the area, the integral of x prime dA? Now, look at, I don't think area is ever going to be 0. So that's not what makes x prime of c equal to 0. This has to be 0. That's a big observation. It just has to be. All right?
X prime equal to 0. That's x prime times.
It's my coordinate. So if I can express this area in the coordinate system x or x prime. Yeah.
If x prime is equal to 0, then x prime times dA is.
But it's a variable that is, you know, all these points in my area have different x prime locations. Yeah. All right. All right. Derive the parallel axis theorem. You ready? Okay, let me do this. I'm almost out of time, so let me do it in equation form. You have to make this observation that y is equal to y prime plus y sub c. That means if I'm given the location of a point in the centroidal coordinate system, and I know the location of that centroid of that coordinate system, or the origin of it, then I can get it in the larger coordinate system, the further away. I'm interested in calculating I sub x, which is the integral of y squared dA. I just substitute for what we figured out y to be. It's y prime plus yc. I expand that, so I get y prime squared, 2 y prime yc, and y sub c. And then I have to remember which one of those are constants that can come outside my integral, because I have 3 integrals. So the y sub c, isn't that a constant? Yeah, so this integral, the integral of y sub c squared dA is just y sub c squared times dA, right? Okay, then this integral is the next easiest one, the integral of y prime squared dA. That's just the definition of my centroidal I sub x. All right, and then this term, the 2 y sub c come outside the integral, the 2 y sub c, and we have the integral of y prime dA. That has to be 0 because y sub c was the centroid. Hence, just by substitution in good math, you get the parallel axis theorem. And I knew I should have gone faster. Once you get the parallel axis theorem, you really can use it when you compute the moments of inertia for a composite area. And we don't have time for that, but I do have a handout for you. Try to solve this problem for next time if you can, as well as doing the homework. Have you been able to do the homework? You see that it's all updated? Thank you very much for your attention. Have a safe weekend.